Okay, here we're looking at a inelastic collision between two birds. This is happening in two dimensions, so we're going to have to consider motion in x and y. It is a fully inelastic collision. The birds are going to stick together and travel as one after the collision. And we have two unknowns. We are asked for the speed and direction. Okay? So what I want to find then is actually the x and y components of the final velocity. So I'm going to have v final x and v final y. I'm going to consider those my unknowns because of the equations that are going to be easier for me to set up and solve. And then these are going to give me the desired magnitude of the final velocity, in other words the speed, which will just look like this. Alright, and that's going to be just v final x squared plus v final y squared, just the two components inside the square root to get the magnitude or the speed. And then the direction, phi, as shown in the figure, is going to be tangent inverse. Well, tangent is opposite over adjacent, so it's going to be the y component over the x component of the final velocity of the combined object, the birds together, traveling as one. Okay, so then we have two unknowns, and we're going to have two equations that are going to allow us to solve this problem. Those two equations are going to be conservation momentum in x and y. So we're just going to have the conservation of momentum using the notation of the problem. This would be the initial in x is going to equal the final in y of the x component vector momentum, and then the same thing. Oh, there we go. So that's just a conservation of x, our momentum in the x direction, and in y, it's going to be quite similar. Initial y equals p final y. Okay, so let's then think about exactly what each of those equations are going to look like. Okay, so in x, what's our initial momentum? Well, we've got that the pigeon is flying entirely in the next direction. So we're going to have mass of the pigeon, so mp times vp, okay? And then, well, what else is going on? Well, the falcon is flying downward, so it has both an x and y component. And so what we're going to have then is v, or mass of the falcon, and then v initial, and then I'm just going to write, so yeah, v initial, we'll just see, because we have, and I'm actually just going to call this vf for falcon, and then I'm just going to put on the cosine of 45 to make it the x component. So essentially this term right here is this one. It's just the initial x component of the falcon velocity. Okay, and multiplied by the mass gives us our initial momentum for the falcon. And then it's going to equal the final component, or the final momentum, and then we're going to have the combined masses, so it's going to be mp for pigeon, mf for falcon, and then times the final velocity, but we want the x component, so that's going to be cosine of phi. Okay, so then we're going to do the same thing in the y direction. Alright, so in the y direction we're just going to have 0 for the pigeon, okay, and for the falcon we'll have m falcon, the magnitude of its velocity, and then sine of 45 to get its y component as initial velocity, and then we have the combined mass, the m total, okay, and then v final, and then sine of phi. Okay, all right. So what we want to do now is solve for I made a big deal that I wanted to solve for the x and y components of the final velocity because this would be easier. Then I went ahead and wrote the angle in there. Well, let's get rid of this and just actually write it as x and y. And you can kind of see maybe at this point why that would be easier. Because that way I don't have to do any trig until the final step where I do an inverse trig function to find phi. Instead I just find the two components as values, just as scalars, and then, it just makes solving the problem easier. Okay? So let's go ahead and solve for the x component first. Okay? So I'm just going to move forward here. And so we're simply going to find that v final x is just going to be mp/vp plus mf/vf cosine 45 all over the combined mass, mp plus mf. Okay? So let's go ahead and plug those values in. Alright, so in the numerator, we're going to have the mass of the pigeon. Alright, so 0.36 kilograms. And that's going to be multiplied by the velocity of the pigeon, a respectable 9 meters per second. Alright, and then we're then going to add the mass of the falcon, which is 0.8, more massive bird, multiplied by its overall velocity, 18, very fast, meters per second. And then we need just its x component, so we're going to have cosine and then 45. Okay, we'll close that off, open up the denominator, and just put our combined masses, which is going to be 0.36 plus 0.8. So we can write here that m total is, let's see, that would be 1.16. Okay, so 1.16. Alright, 1.16. Alright, and then we can close that. Alright, and then we're going to preemptively turn it to degree mode. Alright, and now let's get our value. Alright, so we get 11.6 as the x component of our final velocity for the combined object. 11.6 meters per second. Okay, we're going to do the same thing in y. So v final y, and that's just going to be mf vf sine 45, and then divided by the combined masses, mp plus mf. Okay, so we can just go and modify this equation up here. Right. So 0.8 times 18. Let's change this to a sine. Okay, so that should be fine. Alright, 8.77. Okay. And that makes sense that we'd have a greater x component of the final velocity because there was more motion in x, more momentum. And so it should kind of, the angle should carry through as being smaller than 45. Okay? And that's what we'll see soon enough, the actual value of that. So 8.78 meters per second. Okay, now let's solve for what it explicitly asked for, the speed and the angle. So then the speed is just going to be those two values. So just v final x squared plus v final y squared. Okay, let's do that over here on the calculator. So we'll take this value here, and we're going to square it, and then add, alright, add this one, also squared, and all inside the root. Okay, so 14.5 is our final speed, 14.5, and that's meters per second. Put a box around it. Okay, and then the angle phi is then going to be tangent inverse. Okay, so let's go ahead and do that. Tangent inverse, and I want the y over the x. Okay, so the y component is the 8.7. Okay, let's get our division in there, and then we'll divide by the 11.5. Close our parentheses. Okay. All right, 37.2 degrees. So indeed less than 45 as expected. 37.2 degrees. Okay, energy was not conserved because this is an inelastic collision. However, we were not asked for exactly how much energy was lost. Okay, thank you.